So continuing with our little space station. Oh, of course, as soon as I start recording on cue, someone comes in to interrupt my lesson. So we said this, B says, suppose this astronaut in our space station that we just found needed to have a period of 5.12 seconds, needed to rotate every 5.12 seconds if we wanted to have an 80% gravitational field on the outside. What happens if you start to climb a ladder? So if you started to climb a ladder so that you're ascending towards the middle of the space station, you're going to find that you feel lighter and lighter and lighter and lighter. Your mass isn't changing. What is changing is the normal force, and I've tried to convince you that what you think of as your mass is actually the normal force. So suppose the astronaut begins to climb a ladder that leads to the center of the space station. At what radius will the astronaut feel 30% of his weight? This question's asking for a radius, but we're still going to start out by saying, hey, there is a force pushing him towards the center. We're still going to start out actually with the same equation we started out in part A. We're going to say it's the normal force that's pushing him in a circle. Where circular force is going to be mass times circular acceleration. Don't forget the mass. And the normal I don't know the normal force. Oh, but look. They've told me what I want the normal force to be. What do I want the normal force to be? 30% of his weight. And what's weight? Remember from Physics 11? Another word for weight. Weight is another word for which force? Yeah. So it's going to be, how do we do? Oh, you know what? They're saying 30% of mg. Oh, and conveniently, so I'm going to end up with 0.3 G. I guess a child would feel lighter the same way as an adult would feel lighter. Masses cancel. Which equation do I want to use for centripetal acceleration? Well, what did I figure out in part A on the previous page? You might have to turn back and look. What did I figure out on part A in the previous page? You might have to turn back and look. Sorry? Period. So I'm probably going to want to use the one that has the period in it, which is 4 pi squared r over t squared. What am I trying to find according to this question? Radius, which does appear in my equation. Double check. Do I know all the other variables? Do I know g, 9.8 on the Earth? Do I know t, the period? I figured it out in part A. Cool. So I think let's get the r by itself. It's going to be a little cross multiplying and stuff moving diagonally and things like that. As an equation, what's an expression for the radius? Anyone feel like getting the r by itself? Anyone feel like waking up this morning? Anyone feel like responding? Anyone feel like not drooling? AJ? Oh. Sorry? The radius. I think I said the radius. I want to get the r by itself. Look, the equation's right there. Get the r by itself. Yes, Sasha, help me out here. Yes, keep going. 0.3 g, big T squared. Yes, folks? Stuff we've been doing since Physics 11, right? So let's see. It's going to be 0.3 times 9.8 times, what was the period? Was it 5.12? Yep. 5.12 squared. Now, if we had done this question all in one fell swoop, of course, I would use my answer button, but we found that period a couple of days ago. I doubt that's still stored on your calculator, so 5.12 will have to do. Divided by 4 pi squared. As a matter of fact, I think this actually worked out dead even if we used our answer button, in that you got a nice answer with no forever decimals. We won't this time. 0.3 times 9.8 times 5.12 squared divided by bracket 4 pi squared. About 1.9. In fact, it was exactly 1.95 meters when we used the numbers stored on our calculator in my other block. So as he climbs, when he gets about 1.95 meters from the center, he'll feel 30% of his normal Earth-like weight. Probably do one-armed chin-ups pretty easily, right there. Push-ups would be pretty easy, right there. Dropping things would appear to fall strangely slowly. They would still fall, but it'd be slow. Okay. Example 6. I like example 6. You know what? Is example 6 an amusement park ride? Yep. Is it a cool amusement park ride? Yep. I probably really shouldn't need to say that I like example 6, I like example 6, but I will. And now I have to make a confession. This is embarrassing. I apologize. I've never been on the Gravitron. It's never been at an amusement park that I've gone to. It used to be part of Playland, but then I think Playland sold that one to the P&E, so it's only there in the summer, and I don't go to the P&E very often because I go to Playland every year with my physics students. Going there again in the summer doesn't quite have the pull that it might have as a ride nerd earlier. How many of you have been on the Gravitron, the ride that rotates and the floor drops? You guys have? Okay. I'm jealous. Says this.
I think there was a kind of Gravitron thing that came on the air comes at
Yeah, the kids told me that there was one here too.
Yeah, it was kind of,
So, the Gravitron spins its riders around in a circle. There's several different versions of this ride, so we're going to just analyze the one that stays horizontal. There is also one that slowly rises up. As soon as it's at an angle, the free body diagram is way yuckier, far worse than the parallel perpendicular on a ramp. It's actually much more complicated. Vertically we can handle. In fact, next class we'll look at vertical forces, no problem. But stuff at an angle gets yucky, sorry. So we're going to analyze it horizontally. The Gravitron spins its riders around in a circle. If the ride has a radius of 4.8 meters, about half the width of my room, which is about right, I think, from the size that I've seen. Sometimes they're a little smaller, sometimes they're a little bigger. And it rotates every 2.5 seconds. Let's see. 1001, 1000. I think that's about how long it takes. It's tough to tell because when you're on there, you got the adrenaline rush. You really don't know how fast you're rotating. Your time sense is really screwed up. But I think my numbers are okay. I hope. What is the minimum coefficient of friction required between the riders and the wall of the ride? I guess apparently, according to this question, friction is required. You couldn't make the walls out of ice. That would be a problem. What does this question want me to find? Mu. What's mu? I don't know. What's mu with you? Okay, shut up. Suggestions. Really? Suggestions. This should be instinctive by now. This should be a first reflex by now. Suggestions. I already dotted dolp. Yeah. Before that, suggestions. I'm looking for 3 letters or 3 words. I'm going to do a free body diagram. This is complicated enough that I'm actually, even though they gave me a lovely picture, I'm going to do a complete free body diagram because this is a new experience for me. So I'm going to, over here, represent the person with a dot. Oh, and let's have this person rotating in that direction. So in the picture, they're coming towards us, not away from us. Just, I don't know if that's going to be important or not, Bree, but let's, just in case. Okay? What are the forces acting on this person? Get the obvious one. Gravity. Is this person sliding down the wall? Have you been on the ride? Do you slide down the wall? No. Is this person sliding up the wall? No. I don't think you slide up the wall on the ride either, do you? So I think you're in equilibrium. I think there's another exactly the same size force pointing up. Which force? I'm not convinced, I'm sure, yet. So I'm going to come back to that. Oh, what path is this person tracing out? Circle. Where must there be a net force pointing then? There has to be a force there. What force is that? Jordan, what was that? Oh, are you saying laying against a wall that's vertical is similar to laying down on the floor? We just got to flip our frame of reference. You know what? I think you're right. I think just like the space station, that there is a normal force. And I think that helps me figure out what the mystery force pointing up must be. What must the mystery force pointing up be?
Friction.
Got to be friction. Because friction and normal force, we're always 90 degrees to each other. Friction is what's resisting gravity. Okay. Vertically, everything is in balance. Horizontally, who's winning? There's only one force horizontally, so it's supposed to be a really obvious question. Horizontally, Sean, who's winning? Normal force. So my equation is going to be winner, no loser, equals MA. Oh, but wait. Sean, what path is this person tracing out? I'm not putting, VF minus VI over T or any other expression for acceleration there. This is going to be mass. Which version of the circular acceleration do I want to use? Look at the information that they gave you, and you should be able to figure out which is the best one, because there's two equations for circular acceleration.
Good morning. Please excuse this interruption.
Pause. Which version do I want to use? The one with period in it, because they gave me the period. So that one was 4 pi squared r over t squared. On the left-hand side is the normal force. I don't know the normal force. Oh, and I can't say, oh, but look, there's another force the same size as the normal force, because there is no other force the same size as friction. No, they're in different directions. Don't be assuming they're the same size. Do I know another equation that has normal force in it? What's the only other equation that actually has the normal force in it? Riley, what equation is that? Preach it to me, my friend. What is it? Friction equals mu. You know what? Get the normal force by itself. So you're saying the normal force is friction over mu? I don't know friction. Oh, but look. I know another force the same size as friction. What force has to be the same size as friction? I kind of like this because we're also kind of flipping our standard approach, doing it different. Because normally we've said, I don't know the normal force. Here, turns out I don't know the normal force, but I can use mg over mu. And I can place that right here. Oh, let's go to black so it matches, Mr. Dueck. mg over mu. Oh! What do you notice? When you went on this ride, can a fat person go on this ride just like a skinny person? Can a grown-up go on this ride just like a child? Did you have to step on a scale before you got on this ride? No, you say? Why? What are we trying to find? Where is the, you know what? I'm going to rewrite this because this one's a little ugly. So I have g over mu equals 4 pi squared r over t squared. I'm trying to get the mu by itself. It's on the bottom right now. I can never get something by itself when it's on the bottom. I have to, first thing I want to do is move it to the top. I can use my stuff moves diagonally, can't I? I can move this to there, move that to there, and I think move that 4 pi squared r down to there. Matt, are we good enough to do that all in one step? I think this is, by the way, this unit, this equation is really why already in Physics 11 I started saying it's really worth learning to rewrite these in your head because you can save yourself about 8 lines of work, and to me that's a time saver. So I think we're going to get this. Mu equals You want to try it, Matt? Nu equals what? What's the equation? What's the expression?
P squared,
And the g also on the top, yes?
and then divided by 4
So it's going to be 9.8. What did I say the period was? I've scrolled down.
2.5.
2.5 seconds squared divided by 4 pi squared, and what did I say the radius was? 4.8 meters. I'm hoping I get an answer that looks about right, because I've never been on this ride, so I haven't actually measured any of this. I was kind of making up numbers. I'm hoping for a mu that's between 0 and 1, and hopefully a decimal close to 0.5, but I don't know. Four pi squared times 4.8. You get, oh, even nicer, 0.323.
Yep.
A low mu, now they would probably build in a good safety margin, because that would be exactly when you started to feel yourself almost start to slip, right? That's because that's exactly in equilibrium. So I'm willing to bet they got a coefficient of friction. Who's been on the ride? What's behind you? Is it a rubber cushion? Yeah, okay. So and that polyester rubber, whatever, try rubbing your hand on it. It sticks pretty good. In fact, you can probably get rope burn by. It's almost very similar, I would think, to the what your lab materials are made of, but rougher so that it'll hook with your lab tables are made of. I say lab material. Lab tables are made of, but probably rougher so that it hooks on your clothing, I would imagine. So, hey, I made up good numbers. I'm kind of happy. Now, in real life, by the way, when you're designing the ride, what you would actually do is you would be interested in finding out how fast you had to spin it, because you would have designed the ride, you would know the radius, you would put the fabric on there, you would know the coefficient of friction of the fabric, and when you're designing the ride or you're telling the ride operators, you would say, oh, by the way, you better make sure that it spins every so and so many seconds, otherwise people aren't going to be happy. The gravitron. And of course, if you're really good, you can ride the gravitron like a physics nerd. Of course, this works better when it doesn't take 10 minutes for my, there we go. Let's go name. There's riding the gravitron like a boss. Standing up, trusting the physics. Now, there's something else, and I'm sure none of you ever thought of doing this because you're all nice human beings. There's something else people who have bad physics try and do on that ride. I heard Jordan murmur it to himself. They try and spit. Okay, using principles of physics, if you tried to spit, which way will it go?
Right back at you.
No, that's bad physics. We've already agreed that things aren't being thrown directly away from the center. As soon as it leaves your mouth, what type of velocity does it have? Tangent to the radius. It's going to hit the person next to you, who is probably your friend. Certainly, it's not going to hit the person across from you so that you can somehow make your escape in the confusion when the ride is over and not get beat up. It's going to be the person right next to you, and if their hands are free, have at it, as far as I'm concerned. They should be pummeling you the entire ride. Dumb and Dumber. Oh, last thing, what are the units from you? What are the units from you? Oh, there are none. Okay. We already saw the India circular wall ride. Another example is something called a little toy plane. You've seen these often in dollar stores, in malls, in the entrance. A toy plane is attached to the ceiling via string. It has a propeller which causes it to move in a circle as seen below in side view. If we ignore air resistance and the force from the propeller, so in real life, let's say it's coming towards us, the propeller is pulling it towards us, but air resistance is slowing it down, which is why it's going in a constant speed in a circle. So if we ignore those two forces, which cancel each other out, what's the best free body diagram for the plane? A, B, or C? You know what? Once again, we're going to vote, and once again, it's how high you hold your hand up is how sure you are of the answer. So if you were drawing a free body diagram on that there little toy plane, ignoring the force coming towards us and the force going away from us because they cancel each other out, What would the forces be on that plane? Who says A? Mr. Dueck, it's obviously A. No one. Who says Dueck, it's moving in a circle? It's got to be B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who says, nah, Mr. Dueck, it's C? 1, 2, 3, 4, 5, 6, 7. Who was too lazy to vote? Pick a letter. Gotta have an. I have no problem if you're not sure. The only time I'll get grumpy is if you're scared to guess, because guessing wrong is also learning. Is it not? I know. So, convince me that you're whichever B. It seems to be between B and C. Convince me either that your guess is right or that the other person's opinion is wrong. Convince me. Hey, you know what? Let's draw a free body diagram on this plane. What are the forces acting on this plane? Get the obvious one. I agree. What else? Is there a force pushing the plane outwards? I've tried to convince you that's not the case. Ryan?
I was going to say you leave it like that if you don't draw the other one.
I don't draw the other one. Can you use less pronouns and more proper
I
nouns?
remember what it's called off this, so probably can.
Okay. This right here is FC, which is the net force, which never appears on your free body diagram. Now, wait a minute, Mr. Dueck. You've told me that when I move in a circle, my net force has to be toward the center. How the heck can that be moving towards the center? Are those two forces at angles? Are these two forces at angles? Oh, how would I add those two forces together then? Now watch what happens. If I add them together tip to tail, I get gravity, tension, and the net force, the resultant from the tail of the first to the tip of the second, is towards the center. I didn't need to draw it on the free body diagram. I didn't need to include it in diagram B. It's included in diagram C. There are only two forces acting on it. And those two forces together, like that. It says explain why the others are wrong. You know what? Picture is worth 1,000 words. Or a paragraph. So the key idea in a horizontal circle, your vertical forces are balanced either directly vertically, or if you look at this one, tension has a vertical component which cancels out gravity, and it's got a horizontal component, and that's what's pushing it in a circle. The inwards net force is MAC, which is mv squared over r, or m4 pi squared r over t squared, depending on what information they give you or ask for. And the tangent forces, speeding up and slowing down, are balanced or zero. You're not increasing your speed. So let's look at a couple more examples. Example 8 says, redraw the force diagram and then write force equations for the toy plane. And I said, note, this motion is referred to as a conical pendulum. The conical pendulum is if you have a mass hanging from a string, and if you move it in a circle, can you see it traces an upside-down ice cream cone? Fancy word for cone, conical. It traces it's a conical pendulum, okay? I was trying very hard. I have a little flying pig toy, and I was trying to set it up. I've never been able to get it to work. Someone gave me a new one last year. It apparently will go in a circle, but I'm still mucking around with it. So I was hoping to have one to demonstrate to you. No luck right now. I'll work on it on the weekend and see if I can get it going for next week. Okay? So it says, redraw the force diagram. Okay, what are the forces acting on this little toy plane? What did we say? Get the obvious one? and tension. And then it says write force equations. Okay, let's add these two forces tip to tail. I'm going to have this. Gravity down. How do I know not to stop drawing tension right there? How do I know that's not far enough? Because I know what path is this toy tracing out. A horizontal circle, which means my net force must be horizontally towards the center. That's not horizontally towards the center. That would be wrong. How do I know also not to draw tension that long? Because that is not a net force horizontally towards the center. So, Bree, I can figure out when to stop because I actually know what the answer is supposed to look like. I go, 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 stop right there. There's tension. There is centripetal force. They gave me this angle, which I'm pretty sure is that angle right there. See the Z?
Yep.
Okay. So it said write out force equations. There's going to be three because I think I can write something involving sine, I can write something involving tan, I can write something involving cosine. First of all, how are mg and Fc related? Which trig function relates gravity and centripetal force? Okay, so one equation that comes out of here is tan theta equals what over what? Oh, by the way, or tan theta equals, since Fc is MAC over mg, and oh, lo and behold, Sam, once again, you could also say, I guess, tan theta equals the circular acceleration over 9.8. I think since the mass, by the way, this here, this picture, this is the wave swinger at the P&E, the swing ride. What do you notice happens to the masses? Will an empty swing swing higher, lower, or the same height as a full swing? Same height. Go check it out. You're over there. Okay. How can you relate tension and Fc? Which trig function relates tension and centripetal force? So another equation coming out of here. Sine theta equals Fc over tension. And what relates gravity and tension? Which trig function relates gravity and tension? Which one's left? Huh? Somewhere you're going to see a picture like this in your future. I like this question. I like it. With numbers, though, and I'll ask you to find something. What I'm saying, Riley, is it's nice right angle trig. It's SOHCAHTOA. And there's all sorts of different combinations and equations that come out of here. I think there's going to be one in your homework. I know there's one in the big review package. And I like this question. I like this question. I like this question. Example 9. The picture below shows a frictionless tabletop, maybe like an air hockey table, in top view. The mass is 4.15 kilograms. It's attached to a 2-meter long string, and it's moving at 2.5 meters per second. Write force equations and solve for the string tensions. What are the forces acting on that mass there? Get the obvious one. Gravity. Which way? Well, from a top view, I guess it would be into the page, which is awkward to draw. Is this mass sinking into the page like quicksand? No. Is it flying off the page like Superman? What force is pointing towards us? Normal force. You know what? Since those cancel out, I'm not going to bother labeling them, which is why I'm picking my words carefully. I can't call this a free body diagram because technically a free body diagram is supposed to show every single force acting on an object. But if I'm labeling the forces, you know what? Vertically, everything's imbalanced. Good. Horizontally, what path is this shape tracing out? So where must the net force be pointing? There has to be a force pointing that way. Hey, which force is that?
Tension.
It's a rope. Tension is what's pulling it in a circle. In terms of an equation, tension equals FC, or tension equals MAC. Which A? Give me the equation, please. There's no actual order to them. Yeah. Oh, they gave me a speed. I'm going to use the one with the speed. Thank you. So tension equals mv squared over r. You know what, Callum? This is actually, the tricky part is visualizing what's going on. The actual math is kind of plug and chuggish, really. Because they told me the mass, 4.15. They told me 2.5 squared. And we even have a nice radius of 2. I could almost do this in my head in a pinch. 4.15 times 2.5 squared divided by 2. And I get 12.9, I guess 13.0 newtons? Is that right? Yeah. By the way, if you speed up, what happens to tension? Look at the equation. If V gets bigger, what must happen to the tension? Gets bigger. Now, that's why when you do something like this, you feel like it's tugging against you harder, that you keep thinking that there's a force outwards. No, it's your hand is having to exert a bigger force, and what you're feeling is the Newton's third law, reactive forces come in pairs. You're feeling the force on your hand, which is not what we're ever drawing. We're drawing the force on the spinning object. We already saw the centrifuge game. This is the last one, or we got a couple more? I think 2 more, yes? Woohoo. A blue ball is swung in a horizontal circle, and it completes a single rotation in 1.2 seconds. The cord makes an angle of 35 degrees. Part A asks, what's the centripetal acceleration of the ball? Part B asks, what's the centripetal velocity of the ball? Now, we may need to go all free body diagram-ish here. I don't know, but this isn't actually saying find a force. It's saying find what? What is Part A asking for?
AC.
Centripetal acceleration. You know what? I'm going to start out just writing that equation and see, maybe I have everything I need. Which version of centripetal acceleration do I want to use? The one with a V in it or the one with a T in it?
T.
I know the 4, I know pi squared. Do I know the period? T squared, yeah. Do I know the radius? Do I know the radius? It's not 0.44. Do I know the radius? No. But hey, look at my picture. I think the radius is right there, is it not? And I heard Mark say it's a right angle triangle. He's right. I think I can find the radius actually fairly easily, it turns out. Which trig function? R, opposite, adjacent, or hypotenuse? Opposite. L, hypotenuse. Oh. Sine 35 equals R over 0.44. I guess, actually, I'm not even going to bother typing that in. I'm going to just carry that actually over into the equation over here. I'm going to say, oh, you want the circular acceleration? It's going to be 4 pi squared 0.44 sine 35 divided by 1.2. I could have crunched the numbers for radius, but since it was such an easy expression to transfer over, and I knew I'd have to type it in no matter what, why not just type it in once? All right. What's the centripetal acceleration here? You get 6.92? 6.92 what? Units. It's acceleration. Meters per second squared. It's circular acceleration, but it's still measured in meters per second squared. What's B want me to find? Now, this is the one that is not on your formula sheet, but it comes out of distance over time because you are traveling at a constant speed. Yes, you're accelerating, but that acceleration is changing your direction. What's the distance around a circle? It's called the circumference. That is on your yellow formula sheet somewhere. They actually give you, do they not, AJ, the formula for the circumference of a circle, where they have the quadratic formula and all that other stuff? I think there's a C equals 2 pi r there, is there not? Yeah. Over. You will have to know that we have a symbol for how long it takes to go once around. Okay, so it's going to be 2 pi 0.44 sine 35 divided by the period. How fast is it traveling? How many of you have been, by the way, at Playland on the Revelation, the one that goes in a circle really, really, okay? So if we go, when we are going, you can actually, if anybody goes on that, we can calculate your tangent speed. It's fairly easy to do. You're traveling really fast. Almost, but not quite, freeway legal. You're traveling tangent to the radius really fast. That's why it's a very thrilling ride. This is going to be 2 pi times 0.44 sine 35 divided by 1.2. Bree, I got 1.32. Yeah. 1.32 meters per second. Example 11. I like this question, I like this question, I like this question. But this is a tough one to visualize because I don't have a setup for it. Here's what it's saying. There is a ball, and it's attached, a small ball, and it's attached to a much bigger mass, big M, hanging down through the hole there. And what we're doing, now, if this small ball wasn't spinning, then big M would just, boom, pull it right down into the hole, whack. But what we're saying is this, if you look up, we're saying if you spin this, it'll pull big M, well, it'll pull this one up. You saw it go shooting up. But that only reason it pulls this mass, my example, up is because the spinning mass and the hanging mass are the same. If this one was heavier, Ryan, I could probably find an equilibrium point where it would just hang there quite nicely and I could spin. That's what we're saying is going on here. We're saying we're spinning that top mass at just the right speed so that the force is just right, so that this guy is no longer pulling it down, is not getting tugged up. You're in equilibrium. Is that okay? Oh, and it's saying, how fast? What's the speed of the ball if you want to do that? Okay. Suggestions? Yeah, although this one here, since they gave me two masses and it's a good diagram, it's almost like an Atwood machine, sort of. I'm going to label the forces on here. So I'm going to say, okay, what are the forces acting on big M, the bottom one? Get the obvious one. So we have big M, G. What else? Ah, tension. Cool. I think that's it for the big mass. What about the small mass? What are the forces acting on it? Get the obvious one. Okay, so I have little mg. Now, it's not sinking into the table, and that's because there's a normal force pushing it up. We said, hey, if you're moving in a horizontal circle, our vertical forces will cancel. What else? What path is it tracing out? A circle. So there has to be a force that way. Can you figure out what's pulling it on a circle? Tension. And this is where we're going to depart a little bit from our Atwood machine model, because we're just going to look at the one mass, that top mass. We're going to say, who's winning? Tension equals MAC. Tension equals M, and since they want me to find the speed, I better use the one that has speed in it, v squared over r. Do I know the radius? Yeah. Do I know tension? No. Well, what haven't I done yet? What haven't I used yet? I don't think I've looked at the big mass, big M. Let's go look at that mass. Let's write an equation for that mass. If you were just looking at this, ignore the top part there. Who's winning? It's a trick question. It's a tie. So if you were writing an equation for the bottom one, what could you say? I think you could say tension equals big mg, because it's a tie. Yeah?
Yep.
Oh, and that gives me an expression for tension. I can now say big mg equals mv squared over r. This time the masses don't cancel, which makes sense because if the bottom mass was heavier, I'd have to spin it faster. If the bottom mass was lighter, I'd be able to spin it slower. It does make a difference. What are we trying to find?
V.
Well, let's get the v by itself. Times by r, divide by little m, square root. I think it's going to be big M G R divided by little m, square root. It's going to be big M, 0.036. That's 3.6 times 10 to the negative 2. 9.8. What did I say the radius was? 0.42. Divided by little m, 0.009. That's 9 times 10 to the negative 3, but it's a little less writing. Oh, square root. It's going to be 4 point something. 4.06 meters per second. And that's my centripetal or circular speed. 4.06. If I sped up, you would see that that big mass would slowly start to be climbing up. If I slowed down, that big mass would slowly start to pull it down. What's your homework? So take what I gave you last day, and you can add to it Here we go, here we go, here we go. Come on. So 1, 2, 3, 4. So you could do number 1 now. 2, 3, 4. 5. You can now do 6. 7. 8. You've assigned everything so far. Yeah, I have. 9. Skip 10. 11. Skip 12. You know what? I think it's skip 10 and skip 12. Everything, skip 10, skip 12. So. Oh, I gave you guys number 10 last day, apparently. So it's, and 11. Well, I know, I said everything skip 10, skip. You know what? It's everything, but for you guys, just skip 12. Okay?